All right, ladies and gentlemen, and everyone, looking at solving some polynomial equations today. Kind of an odd video for us here, just because of the design of the note. I want to point out some things about how we knew to solve a linear equation, how we know to solve quadratic equations, and obviously when we're using those skills, we've been using those skills all year. You have been using those skills since grade 9 for linear equations, grade 10 for quadratic equations. So what I'm actually going to ask you to do, I know we're only about 30 seconds in here, is pause the video and go through the first page of this note. You should be able to work your way through the entire first page and then come back and double check your own solutions, and we'll go through this together. I just want to point out some things in our solutions more so than go through the solutions together. I think that would be a bit of a waste of our time. So pause the video here, and in about 5 seconds the video will forward to the filled in version of the page. Good, so nice and easy. We're looking at solving a linear equation. This might not immediately look like a linear equation at first glance, but if we pay attention to it, we realize that there's only ever a term with degree 1 or order 1. With the highest exponent is a 1 here. We simply rearrange. We know how to work with this. We distribute. We use our distributive property to distribute this 4 into the brackets. We isolate for x. We find that x equals -5. We should know how to do this. This honestly should be second nature to you by now. Now, what we're doing here, we're simplifying both sides, and then we're using inverse operations. We're able to use inverse operations here because after we simplify, our variable, our x, only shows up once in this equation, right? I know it shows up 1, 2, 3 times in the first line, but we're quickly able to collect our like terms, simplify it very quickly. It shows up once, then we can use our inverse operations. We divide by -3 from the 4th line to the 5th line. That's how we do it, nice and simply. Okay, again, we're just, I'm not expecting you to have been posed any challenge by this problem here, but we are going to rely on the skills that we have used in other years. Next, example 2. Okay, 2a, nice and easy. Looking at grade 10 skills here. Again, we've been using these skills for a long time. In particular, during section 3.6, we were factoring to finish off our problems. In fact, we know how to factor polynomials of a higher degree than this by now. But this one's a nice, simple trinomial. Once we factor it, we're able to set each factor to 0 and then isolate for our variables to find the roots. Remember, if a question is asking, and I could have explained this in the first one, if a question just tells you to solve, what they mean by that is they want you to find x values that make the equation true, or make the statement true, right? Where this is a mathematical statement. They're saying, okay, well, for which values of x is this true? And we find here, well, if x equals -3, it's true, or if x equals -4, it's true as well. Now looking forward into example B here, it's a little bit tougher, right? We can rearrange this off the start. We can put all of our terms on one side of the equal sign, and we might realize, okay, this one doesn't factor, right? It's a simple trinomial, so we can check it very quickly. We now have a very systemic way to do that. We check the factors of -7, and that's plus or minus 1 plus or minus 7. If we want, we could use our factor theorem through here. We can quickly see that this does not factor. Okay, if it doesn't factor, then we need to throw it into the quadratic formula. So hopefully you should be a master of that by now. If not, you can look that one up on your own. There are plenty of fantastic resources to walk you through using the quadratic formula. And you can use this quadratic formula here to find your final roots. This is 2 roots, right? Plus or minus the square root of 53. So 5 plus or minus the square root of 53, all divided by 2. Now, what we want to pay attention to here is when we're factoring this, when we're finding the roots, since we're working algebraically, right? There's no contextual problem here that we're working with. Then we want to leave our final answer, and hopefully you have become a little more comfortable with this as you've worked through your math careers. We want to leave our final answer in exact form here, right? We're not throwing this into our calculator. That's not useful to us. We need to leave our answer in exact form. That means we leave the radical as is. This one is what we call an irrational root. Now, again, to break that down, if we are able to, then we want to solve a quadratic using inverse operations, right? Now, there was not an example of that here. Neither of these were in vertex form, but we should know how to do that. That actually looks very much like example 1 up here, where after rearranging, we only see our variable appearing once. If it only appears once, then we're able to use our inverse operations. Now, if we can't use our inverse operations, we can solve a question by factoring. And if we cannot factor it, then we have to use the quadratic formula. In general, if we can avoid using the quadratic formula, we like to because it can sometimes end up being a little bit messy, and the other approaches are usually quicker for us to handle. Now, I'm hoping you're feeling pretty good about your math skills at this point. We're going to jump into how we can solve our equation if our polynomial has a higher degree. In this case, degrees 3 or 4, but we could solve polynomials to much higher degrees as well. Again, folks, we can use our inverse operations if our variable appears more than once. Okay, that's going to help us out. Sometimes we're able to jump right in with our inverse operations and solve a problem very, very easily. And if in that case, we might be looking at if we have a function. Let me see here, an equation. Let's say 3 equals 2x minus 6 squared. Nope, sorry, to the power of 3 minus 4. Then we could solve this here by isolating for our x, because x only appears once, and that's the key, right? So we add 4 to both sides. That's 7 equals 2 times x minus 6 cubed. That is 7 over 2 equals x minus 6 cubed. And then we can take the cubic root of 7 over 2 equals x minus 6. And you can see very quickly, I'm just going over this extremely quickly because honestly, it should pretty much be review for this point, how we're isolating for a single variable, where x equals the cubic root of 7 over 2 plus 6. Good. Again, that was just an aside. We will we'll clear that up so we have this the space to handle what we're working on over here. If we're not able to use our inverse operations, what we want to work with is we want to rearrange our equation so that it's a polynomial set equal to 0. Okay, so that's like 2a. We rearrange the equation so it's a polynomial equals 0. And then 2b, we factor it. Luckily, we know how to factor these. We've been doing that since section 3.6. We're masters now. So we can take a look here. Okay, how many terms do I have in total? I have 5. Right, I have 1, 2, 3 on the left side, 4, 5 in total. Now we can rearrange this so that it's a polynomial equal to 0. Okay, nice and easy. I see 2 negative terms over here. I can add them to my other side. So that means I'm working with x cubed plus 10x squared plus 15 plus 3 plus 27x equals 0. Right, nice and easy. Now that it's equal to 0, I can simplify it further. It's a good idea too. So I'm working with x cubed plus 10x squared plus 27x plus 18. Again, it's still equal to 0. I don't need to write that. Remember, if it's left blank, then it's assumed that it's equal to what's written up above. Okay, so fantastic. Now what we can do is we can kind of set f at x equal to this left-hand side. This is kind of a formality. This is so that we can use our factor theorems. So it sets us up for the notation that we will use above. So let's set f at x equal to x cubed plus 10x squared plus 27x plus 18. Okay, so if we're setting it there, then we can check our possible zeros, right? That's the first step if we're factoring a function here. So our possible zeros or possible roots, we're working with the factors of 18 divided by the factors of 1. right? That's our hidden leading coefficient. So nice and easy, the factors of 18, we're working with plus or minus 1, 2, 3, 4, not 4, not 5, yes, 6, and 18. 9 and 18. Okay, nice and easy. Now here we can sort of, I want you to stare at this right now. I want you to stare at the polynomial for 10 seconds. I want you to stare at these possible roots and just try and think, are there going to be any answers that I already know? If I'm checking them out, if I'm doing step 2 where I'm testing my possible roots, are there any possible roots that I don't even need to check on right here? Let's think about it. Well, what I have, this polynomial f at x, all of these coefficients have something in common. All of these coefficients are positive. Okay, well, if I add up 5 positive numbers, there's no way it's going to equal 0. So right off the start, I can eliminate half of my possible zeros. If you don't follow that, that's okay, but I want you to go back, rewind it, listen to it again, and see if it adds up for you. Because now we can work with only 6 possible roots rather than 12 right off the start. Either way, we should be able to solve it. We can check it out. We can try f at 1. We can try f at, whoops, no point in trying f at 1. Well, we can try f at -1. Okay, f at -1, we're working with -1 cubed plus 10 times -1 squared plus 27 times -1 plus 18. Okay, nice and easy. That's -1 plus 10 minus 27 plus 18. Well, boy, if I do that nice and quickly in my head, it looks like that equals 0. Okay, if that equals 0, we'll put together our conclusion here. Okay, so then since f at -1 equals 0, x plus 1 is a factor. Awesome. Okay, so if x plus 1 is a factor, and that's by the factor theorem, then we can work forward. We know how to do this. We are masters of this. We've already written an assessment on it. I apologize for not leaving you enough space here. We'll keep going. We know how to factor this. Whoops. We're working with the coefficients, and that is 1, 10, 27, and 18. My root is -1. So 1, -1. Again, you should be a master of this by now. Pause this, practice it on your own, and then come back and confirm your answer with mine. Oops. 9, -9, 18, -18, 0. This is a 0. That makes sense because it's a factor. Here's my quotient and my multiplication statement. I'm working with x cubed plus 10x squared plus 27 plus 27x plus 18 is equal to x plus 1. That's my divisor times my quotient, which is x squared plus 9x plus 18. Like above, we can factor this even further just by handling it like a simple trinomial. So that's x plus 1, x plus 3, x plus 6. Okay, here's my equation factored. Now then I need to ask myself, okay, what's the implication of factoring this problem? Let's allow me to resize this here. What's the implication of factoring this problem? Right, I'm not finished. It was my goal to find solutions. I haven't found solutions yet. I've just found factors. I need to remember that in my problem, f at x equals 0, right? If I come back up here, I'm working with what I called f at x over here on the left side. This is equal to, on the right-hand side, 0. Okay, well, I know how to work with 0 after I've factored it, right? So I know set f at x equal to 0. So I'm working with 0 equals x plus 1, x plus 3, x plus 6. And that means that any of my factors can be set equal to 0. That means that I'm working with x equals -1, or x equals -3, or x equals -6. These are my solutions. This is my final answer. Now, this might look, perhaps that took 5-6 minutes of video time here, and I did go through it pretty quickly. But of this, the only part that's new, folks, the only part that's new is rearranging it equal to 0, which you've done before. That just means we're putting it in standard form, and deciding to call it f of x. Right now, deciding to call it f of x, all that does is it lets us use this notation down here. When we're factoring it, it lets us use this f of x notation. It lets us quickly say what we're doing. But if that makes you uncomfortable, just try it out. Just try and follow along. This is important as we set up the formal solution here. Okay, so that you should be able, I'm hoping you were able to follow that entire process here. We're going to look forward a little bit further, and we'll work with some other problems. We're not necessarily going to rely on our factor theorem every time. Here we'll work on example, I think it's 2b, 3b. Okay, so x to the power of 4 plus x to the power of 2 equals 12. The first step, again, like before, we rearrange so that one side equals 0. So that means x to the power of 4 plus x to the power of 2 minus 12 equals 0. This here, could we use our factor theorem for this? Yes, absolutely. We could try and use that. We could try and find some factors. Do we have to do that? No. We can rely on our grade 10 factoring skills. So I'm going to leave this for you. Grade 10 factoring skills. Try it out. The final answer will be uploaded to the classroom. Okay, now C, I realize I didn't leave you much space. You know what? I will adjust the notes so that you have more space here. 3C as well, grade 10 factoring skills can help you out. All right, so I'm not going to solve that one either. Example 3D, grade 10 factoring skills. I'll leave these for you. You're able to practice your grade 10 factoring skills with these here. Try them out. Again, solutions will be on the classroom. And lastly, we can look at the implications of this function having a root at x equals -1/2. All right, so nice and easy. Let's try and put this together. I know we practiced these a little bit here. And we'll work with what is the implication of it? What does it mean if there's a root at x equals -1/2? Well, that means that we have a factor, x equals -1/2, and we can basically unisolate. We can collect all of our terms on one side so that there's a 0 on one side. That means x plus 1/2 equals 0. And if I want to rearrange that further, that is 2x plus 1 equals 0, and that is one of my factors. Okay, well, if that's one of my factors, that's well and great. What does that mean? Right? Well, what that means is something that we're going to come back to later. Well, we ask ourselves, if it has a root here, we can throw that right into our factor theorem, right? So by our factor theorem, and that means if we use the logic from our factor theorem, then it tells us f at -1/2 equals 0. Easy. Okay, well, f at -1/2, I know what that is. F at -1/2, that's 2 times -1/2 cubed, right, where I'm drawing on this right here, plus -1/2 squared minus 3 times k times -1/2 minus 9. And then we can rearrange this to isolate for k. I want you to try that out here. Pause the video, try it out. And come back and you should find that k equals 6. Okay, well, if k equals 6, we need to look at the rest of the problem, determine the value of k, done, and then determine the other roots. We know how to do that now, right? We can factor our problem. We're working with this polynomial up here. We can factor out our 2x plus 1. We're working with f at x now equals 2x cubed plus x squared minus 3 times 6x minus 9. And that is 2 times x cubed plus x squared minus 18x minus 9. We can factor out our 2x plus 1 that we found earlier in our solution to come up with our final answer, again, which will be posted on the Brightspace classroom. All right, so now I'm hoping, folks, you are feeling a little bit more comfortable solving polynomial equations, knowing what that means, and relying on our factoring skills to do so. We'll go a little bit into more detail in section 4.2. What happens if it's not an equal sign in the middle, or if we're working with other such relations.